Section 9.2 in the Klein's textbook talks about energies and equilibrium and temperature. And let's just pick cyclohexene once again. And as I mentioned, this contains a pi bond. And a pi bond is worth 83 kilocalories per mole. Okay, Klein is an old school textbook kind of thing, so we're using kilocalories rather than the recommended metric joules here. Now that doesn't count the single bond as well. It's only the double bond that's breaking here. And then if we react this with HCl, okay, this sigma bond here is worth 103 kilocalories per mole. I'll just leave the units off from now on. And what you form as a product is going to be, so the pi bond breaks and you form a carbon-hydrogen bond. That value is 101, okay? And this carbon-chlorine bond is being formed, and that value is 84 kilocalories per mole. So remember that the delta H for a reaction is the sum of the bonds broken minus the sum of the bonds formed. Okay, so what we have on the left are two bonds that are being broken. And so, I'm sorry, that should have been a 63, not an 83. So the sum of the bonds formed here is 166, okay, kilocalories per mole. And the sum of the bonds formed is 185, okay? And you can see how this number is going to be negative. And that means that the reaction goes from left to right, and the products on the right are strongly favored, okay? That's a huge number, okay? So this reaction is 100% products and 0% reactants at equilibrium. Now, another concept, so that this describes the energies and the equilibrium, okay? These are all downhill reactions. So if we sketch a reaction coordinate diagram, we would get something like this, okay? Here would be your starting materials. Here would be your products. Okay, there's some kind of transition states or a single transition state in between, and it's all going to favor the products at the end of the chemical reaction, okay? So this is a reaction coordinate diagram showing energy and reaction progress. Now, another thing to think about is temperature dependence. It is possible for an alkene to react with hydrochloric acid to form, I'll just simplify this and write chlorocyclohexane, and it is possible for chlorocyclohexane to react to form cyclohexene. So this top reaction we call an addition reaction. Okay, and addition reactions are favored at low temperature. I meant to say low. Now, why is that? It's because you're going from two particles, right? You have cyclohexene, and you have hydrochloric acid, and you're going to chlorocyclohexane. So you have two particles going to one, and it has to do with the Gibbs equation, okay? And when there's more order or less randomness, delta S is positive. And so if we do this at a low temperature, negative, I mean, delta S is negative here. That means that if you do this at a low temperature, it's going to be more favored, okay? The reaction here, you're actually producing maybe hydrochloric acid or some other things. So you're going from one particle to two particles, and due to the entropy arguments here, this is going to be favored by high temperature. Okay. So we don't indicate that too much in a chemical reaction, but if we were to do this in the lab, we wouldn't boil this or anything. We do this at room temperature. We might write RT under the arrow. We might write 0 degrees Celsius, maybe even -20 or something. We have different ways of chilling reactions. Okay, but that's just something to think about. When we do the reaction in the lab, we're actually taking terpetal alcohol and we're doing an elimination reaction. We're doing a substitution reaction to get the chlorinated product here. And we don't want this molecule to give us the alkene, okay? And that would happen at high temperature. So we use ice, okay? We use ice to make sure that this reaction does not occur. And we favor only one product over the other. And it all has to do with entropy.